Alright, hello and welcome back. We got a bit mathy last week, and we're gonna get a bit more mathy, but translate some things into code as well and show that programs can be proofs, which is odd, but very nice. So maybe I should talk about a little bit what we were discussing last time. Just remember these two symbols, that's the big deal. So this upside down A means for all, and this mirrored E means there exists, and they are mathematical things that we can use to prove stuff with. And we talked about what it means to be sorted, how to describe something that we take for granted maybe with math. Okay, so for all lists L, for all indices I, if L of I is less than or equal to L of I plus 1, this is what it means to be sorted. Okay, if you can prove this statement to me, then we have a sorted list at our hands. Okay? So, one way to prove things is to actually write code, which is fun. So, let's go all the way now. Let's go from English to the predicates that we were talking about, involving quantifiers, and let's turn some stuff into code. So I'm gonna break a rule today, in that I'm gonna start programming a little bit. Even though I don't normally do that in these first lectures, do I? Alright, so let's move on to our first example now. So let's translate this into a predicate. Find a prime number that's greater than 50. What does it mean to find a prime number that's greater than 50? Okay, so in order to make this math, we have to introduce a variable, right? We've got to talk about this, this thing that we want to find. So let's call that number that we're looking for x. Okay, so what is true now about x? Well, we know a couple of things. We know that it's greater than 50, and we know that it's a prime number. Those two things combined is all we really have at the moment. So x is greater than 50, and x is prime. Okay, that's nice. This is not quite yet math, but ooh, we see something interesting here. And we can make that a bit more mathy by changing that into a symbol, can't we? Let's do that. So x is greater than 50, and x is prime. Okay? So that's what is true about this number x, if it exists, if we can find it. Okay? So we want to prove that there's a prime number that's greater than 50. So we're almost there. If we can find that x, for which this stuff is true, then the following statement is true. And I guess really I should have put this whole thing like that. That was kind of weird. So find a prime number means show that there is one, show that it exists. Okay? So there exists an x, x is greater than 50, and it's prime. And this notation, it looks like a function call, doesn't it? It's like a function call in math. Yeah, I don't know why that got so not thick. Okay. And so you can pretend that, we would want it to return true for this x in math language, not Python. For the correct x, if x happened to be prime. Okay, so if we can find that x, then we have proven the following statement. There exists an x. We just found it. Here it is. It's greater than 50 and it's prime. Okay? And that's the final piece of the puzzle. We have to introduce this quantifier over x. So this actually introduces the variable x. So that we can then talk about it. And that's the last key thing about these quantifiers. Every quantifier introduces a brand new variable. You can't use a variable without it. So if we go back up here maybe, for example, if I were to get rid of these two things, then suddenly we don't know what L means, we don't know what I means, because they're just random things. They're symbols. But if we include these quantifiers now, we know what we're talking about. Oh, these are supposed to be lists. Take any one of them, plug it in. These are supposed to be indices. Take any one of them, plug it in. And this is always going to be true. That's a very strong statement, and that's what it means to be quantified. Universally quantified is what the for all means. All right, so, okay, with all of that, we want to prove this statement. We want to find a prime number that's greater than 50. Oh, sorry, not the smallest prime number. That's a bit harder. Find a prime number. There we go. All right, so you can actually make a program to do this, which is weird and exciting. So what is the strategy? What's the algorithm that you'd use to find a prime number that's greater than 50? How would you prove this? Assume that you have a isPrime function that'll return true or false, depending on whether your number is prime that you give it. Well, what if you just make a variable, start it at 51, and keep on checking, is prime I? Does that make sense? In a loop. And like, okay, 51, if 51 wasn't prime, let's try 52. Let's try 53. I guess technically we can only try odd numbers and it would still be correct. It'd be a bit faster, I guess. So you keep going like that. Okay, so that's our pseudocode. You'd iterate through all the numbers starting at 50. I guess technically 51 would work, because we're greater than, strictly greater than 50. Perhaps we can call the current number z, or I guess I'm calling it I in my example, so I'll call it I. And then we'll just keep on seeing, well, is I prime? If it is, stop. And that's the last cool new thing. Programs. You can write a program to prove a statement, okay? Which is very interesting and very powerful. So programs can actually be proofs. All right, so here I go breaking my rule. I'm going to write this isPrime function, and then we're going to prove that there's a prime number greater than 50, okay, by finding it. All right, honestly, it might be 51, I'm not sure. We will find out very quickly. So let's make a new file. Let's write an isPrime function. So it's going to take a number n, and returns true if it's prime. It returns false otherwise. So we can use an if statement based on the result of this function. Okay? So how do you test for whether a number is prime, you might ask? Well, what does it mean for a number to be prime? A number is prime if the only factors, the only things that divide cleanly into it are it and 1, right? So like 7 is prime because only 7 and 1 divide cleanly into it. That's how we say it. 4, for example, is not prime because it has a number other than 1 and 4 that divides into it, namely 2. Okay, so if we search through every possible number between, I don't know, 2 and the number minus 1, then we've figured out if something's prime. So here's a way to search for primeness. Two and n minus 1, and seeing if that number divides cleanly into n. Okay, and divides cleanly, another way of talking about that is there's no remainder. So another way to say divides cleanly is there's no remainder when you divide. Okay, so now we can use the modulus operator, if you remember that gets the remainder. So if I give you an example in the REPL just quickly, here is 4 remainder 2. it goes in cleanly, 0. Here's 15 remainder, 15 mod 4, remainder 3, because it's 12 remainder 3. 15 divided by 4 is 12 and 3/4. Okay, so we can use this modulus operator to get the remainder. Okay, so use mod to get remainder and see if it's 0. Alright, so let's try all the numbers between 2 and n-1. How do we do that? Well, we can use range 2 and then the number n, like maybe it was 42. This would go all the way from 2 to 41. Right. Because of the weird way range works, it doesn't consider the last number. It goes just up until the last number. Okay, so we can say for I in range 2 n-1, now we have an I to talk about. Okay, this for loop's going to iterate, and I will be set to every possible number once. So the first time I will be set to 2, then the next time I will be set to 3, and then the body of this loop will execute. Okay? So let's check. So if n mod I is 0, so if it divides cleanly, if there's no remainder, then we say true. Oh, sorry, we say false. This can't be a prime number. Because something other than n and 1 divided into it, because we tried all the ones in between n and 1. And something divided cleanly, so definitely this is not a prime number. Okay? So this function takes a while if you give it a big number, because it's got to try every number there. Okay, otherwise, if we got this far without returning, without saying no, we tried every number. And still it was okay. So that means the number is prime. Okay, and we can return true in that case. It's okay to return in 2 different places. That's totally fine. Okay, so that's our isPrime function. So I save that and I can print isPrime 42 and isPrime 7. No, let's save it. Let's call it primes.py. How about that? I'm gonna run it. So we get false true. Very nice. It looks like it's working. Those were our tests. So now we want to try all the numbers starting at 51 and seeing which one is prime. Okay? So now let's just start at 50 for fun. Okay, so here's how we can do that. We can use a while loop, perhaps. We can say, let's not use I, let's use j. J equals 50. It starts at 50. While j is, I don't know, less than or equal to 100. Or you know what? Let's just keep on going. While true. No, let's try until 100 maybe. J is less than or equal to 100. We could say print j. Maybe if it's prime. How about we do that? We'll say j comma is prime. If it's prime. If is prime j. Okay. And then of course we have to increment j each time. Alright, so here's what I'm doing. I'm making this variable called j. I'm going to keep on increasing it, so j is going to be 50 the first time, 51 the second time, 52, and so on, until it gets to 100. It's going to keep on trying. We're going to check if j is prime and print it out if it is. Alright, so drum roll please. Oh man, so 51 wasn't prime apparently, but 53 was. That was the smallest number greater than 50. That was prime. But all of these prove that there is a prime number greater than 50. We didn't say which one. We just said it was greater than 50. So here are all the ones. Here are all the possibilities that we have between 50 and 100 that are prime numbers. Okay, so that was really fun. I hope that's making sense in your mind. Like, we can take English, change it into a predicate, and actually go and prove that predicate, sometimes by writing a program, which is super fun. Okay, let's try another one. Prove that for all numbers n between 0 and 100, n is less than or equal to 10. Okay, how shall we do this? So again, we need to make some math out of this. So for all numbers n between 0 and 100, square root of n is less than or equal to 10. What does that mean? So I see a for all. That's going to be helpful. We'll use that. N can be the variable that we use. We're going to somehow have to track whether or not our number is in the proper range. We'll have to be like, okay, n, the n that we're considering, it's going to be greater than or equal to 0, and it's going to be less than or equal to 100. Okay, and then n, its square root is less than or equal to 10. So a lot of things that we have to maybe and together. So here we go. So here's how we can check a range. We can use if. And you know what if translates to? It translates to a implication. So if n is greater than or equal to 0 and it's less than or equal to 100, then the square root of n is less than or equal to 10. So that's what we're trying to prove, okay? So I want to prove this. That's always what we're trying to prove. Okay, so let's make this more mathy now. Let's introduce some things. So how are we going to do that? We need definitely that implication, and eventually we're going to need a for all. Okay? So here's how we make the range. N is greater than 0 and is less than 100. If all of this is true, I guess I should use parentheses to just highlight the fact that this is all the if part. So if all this, then this thing is true. Okay? That's what we can convert it like that. So then we have this math, and then we need to still quantify over n, because we don't know what n is right now. We got to add it in, and then finally, here we have it. Boop. So for all n, if n is greater than 0 and n is less than or equal to 100, then square root of n is less than or equal to 10. So this is what it means in English again. So very specific English. This translates to, for all n, if n is greater than 0 and n is less than or equal to 100, then, and I'll have to make this smaller in a second, we're almost home, then the square root of n is less than or equal to 10. So does this match what we were trying to initially prove? And I don't know. Why won't that work? And the answer is yes. Okay, so this long sentence is precisely, that's the word I'm looking for. So this statement is precisely this small one down here. Okay, so very nice. Again, now we can convert this to pseudocode, or just real code eventually. And so pseudocode is just Englishy Python. That's all it is. You can translate it to any program, in fact, any language, in fact. So here's how we can convert this, again, to pseudocode. We have to prove that every number n between 0 and 100 is less than or equal to 10 when you square root. Okay, we can do that. We can try every number. So for all means try everything. It better be true for all the numbers. We can just try them all. All right, loop through every number, and between 0 and 100 we can use a for loop, we can use a while loop. If we take the square root and it's greater than 10, we can stop and be like, oh, false. No, that means this wasn't true for one of those numbers. Okay? That wasn't true for a certain number. That's unfortunate. That would prove our statement is false. Otherwise, if we get far enough without ever printing false, we can print true. Okay? Print true if we ever, if we don't ever say false. Okay. So we can convert this again to code. We could say, okay, make a new file. We can say, all right, can I get this slightly like that? Okay, so here's the idea. Loop through every number between 0 and 100. So for I in, or let's use a while loop, why not? I equals 0 while I is less than or equal to 100. Do stuff in addition to doing I equals I plus 1. Okay, so now let's check if our current number, its square root, is less than or equal to 10. Okay, so if, and so now I have to use square root, which is in the math library. We say math.square root x. Okay, so I got to import math. If square root I got to put a math dot in front of that, is less than or equal to 10, we're home free. So we want to check if it's not. Okay? Maybe I should be saying check whether. So if it's greater than 10, then we have a problem. Okay? Print false. And then maybe I can save in a variable like is false equals true. Or that's kind of confusing. Maybe I can say is true equals false. Either way, it's hard. So originally, at the very beginning, we're hopeful. So we'll pretend our proof is innocent until proven false. It's true until proven false. So we'll say is true equals true. And then, only if we ever need to, we'll change it to false. And then we'll check it down here. If is true, we can print true. Which is funny. So here's how this is working. We're taking I again. We're starting at 0. We're going all the way from 1, all the way to 100, inclusive. And we're trying the square root of this I every time, making sure that's less than or equal to 10, but we're also keeping track of this is true variable. And it starts out being true. Eventually, if we find a number that doesn't hold up to our case, we'll have to say false. We'll say, oh no, finally we found a counterexample. Our proof is not true. But it's quite possible that it is, in which case we'll keep this true, and at the very end, if we haven't proved ourselves wrong, if we haven't found a counterexample, the proof is true. The proof holds, we say. Okay, so this is square root less than example. How about that? So this is going to try every number, printing false if we find a bad number, and true otherwise. Oh man, was this a true statement. It is true that for every number between 0 and 100, the square root of that number is less than or equal to 10. It's not true for 9, so if I replaced this with 9, then it would be false. Then it's not true. Not provable. Let's try that. Let's be like, okay, I want to see if it's possible, if it's true, that every number is less than or equal to 9 between 1 and 100. So this would be less than or equal to 9. If it's greater than 9, we have a problem. And we have a few problems. You see that? And we won't print that it's true. Okay, I hope this is making sense. This is true variable. The fact that we're setting it to false might be a bit confusing, but hopefully you understand what it's doing. It's just checking, hey, did we find a counterexample? Okay. Let's get this back to how it was, and that's that. So I guess what I want to say here is that logic is really fun. It existed before the field of computer science did, and we've definitely borrowed heavily on it. But logic and computer science, they are better together if you use both. Not only can you write programs that might be correct, you can write programs that are definitely correct, okay? Because you can test them, okay? You can write programs to confirm that your programs are correct. Which is beautiful. And otherwise, you can argue that the ones that you do have are not correct. Okay, you can find counterexamples using the same method of writing programs. And so people have been writing proofs a whole lot easier thanks to computers. We found a number of new discoveries just because we have a lot of processing power these days. So I don't want to continue with like the next lecture yet because we've taken up a lot of time, and I know you have a large essay that's about to be due. So I'm going to stop here, and I'm going to write up your next essay assignment. So stay tuned for that. I'll be right back. And yeah, we'll end a little bit early today. Okay, let me explain your essay, and then we'll get you out of here so you can go and work on the longer essay that's due this week. So you have absolutely no excuse to not get it in and make it perfect. So here is your next essay after this one. It'll be a 750-word essay, and here is the prompt. So it's about beauty, in fact, and it's more of a philosophical essay, I guess. So go ahead and pick your favorite painting, or find one if you don't have one, that was made sometime before 1900. So you can choose from many, many different kinds of art that has been around for quite some time. Now assume that the artist who made that painting was alive today instead, and created the same painting on a computer. Okay, so on a computer using today's technology. So they had like a drawing tablet like I do and I use in class. They were using Photoshop. So they were doing all the same stuff. They were using brushes. They were just virtual ones, virtual brushes, virtual color. Would that painting still be beautiful in your mind? Would it still seem as beautiful to you? And I want you to explain your opinion. You could say, yes, I think it's great still. Or no, there are some differences now. So I want you to pick apart your brain, analyze what you're thinking, and explain your feelings. So just write 750 words about this prompt, and please cite at least one work in this essay. It doesn't have to be anything in particular. If you want to cite a painting, go for it. So here are some useful sources on the subject if you'd like to read up about it. I'm not sure which side any of these lean, but it's good to see both sides probably of this argument. And if you don't know anything about digital art in general, like that's something that you're not very familiar with, here are two people that I follow on Instagram that I enjoy. So you can see the kinds of possibilities that digital art gives you. And then everything else is the same. I'm going to give you 2 weeks to do this. And yeah, have fun. Hopefully it's exciting to analyze and talk about. So with that, I will see you in the programming lecture.